So now that you can write atomic symbols for any species, you kind of starting to get familiar with the periodic table. We have one last thing to talk about, and that's the concept of isotopes. Now, every element can exist in more than one isotope many times. And an isotope is an atom of an element that has a different number of neutrons. So for example, let's look at hydrogen. Hydrogen exists in 3 isotopes. Now, only 2 are listed in the table here. Those are the 2 more common ones. The first, the hydrogen that contains only 1 proton and 0 neutrons, this is hydrogen. Hydrogen can also have 1 proton and 1 neutron. This is called deuterium. And then hydrogen can also, the radioactive isotope, can have 2 neutrons and 1 proton. And this is called tritium. Now, notice the abundance of hydrogen, this is 99.99% of all hydrogen atoms. This is about 0.01% of all hydrogen atoms, and essentially tritium exists around never 0% or so. But these all have different properties from each other and have different uses. For example, when you're studying large biomolecules and you want to say like some protein or some enzyme, you want to investigate the structure of an active site. We can use this thing called NMR, which is called nuclear magnetic resonance. Well, a lot of times we look at proton NMR, so it looks at all the hydrogens. And if we want your signal to just focus on the active site, what we can do is we can swap out all the hydrogens in the molecule with deuterium, except for the ones at the active site. And when you do your run your spectroscopy, you can just look at the spectra from your active site and get a better feel for the structure and what's going on. And we see that carbon has 2 main isotopes. Oxygen has 3 here. Chlorine has 2. Potassium has 3 main isotopes. You can look up tables of this information on the internet. Now, if you go back to the periodic table, and you look at each cell in the periodic table, what does the cell represent? So I'm going to stop on, say, carbon here. Notice it says 12.011. Now, that represents not the mass of one atom of a carbon, but the average atomic mass of carbon based on the abundances of each of the isotopes. Because we really should expect the mass of an atom of carbon to have an integer mass, because protons and neutrons both have a mass about 1. Okay, that 0.011 comes from the fact that there's a couple isotopes of carbon that exist in different abundances in nature. So how do we interpret this? Let's look at chlorine. Okay, we have 2 isotopes of chlorine, chlorine 35 and chlorine 37, and I'm going to go to 1 decimal place, so then when I do my calculation, you should use as good data as you can. That way I don't have to flip back and forth. So we have 2 isotopes of chlorine, chlorine 35 and chlorine 37. And here's what I'm going to do. I'm going to say chlorine 35 has a mass of 35.0 AMU, and chlorine 37 has a mass of 37 AMU. Now, I'm going to look back at the previous slide to get the relative abundance. On chlorine 35, 75.7. Oops, wrong way. Oops, sorry. Wrong button there. There we go. 75.7%. And then 75.8 and 24.2. Let me just make this an 8 here. 75.8% and then 24.2%. Now, like I said, you need to take more sig figs. How do we calculate the average atomic mass of chlorine? What you do is you take the abundance of the first isotope times by the mass of that isotope plus the percent abundance of the second isotope times the mass of the second isotope. And you do this for all the isotopes that you know of for your compound, or for your element. For chlorine, what we're going to get is we're going to find that we get 35.0 AMU times 0.758 plus 37.0 AMU times 0.242. Make sure you convert your percent into a decimal, otherwise you're going to get some ridiculously large number in the thousands and it's going to make no sense. And then you run it in your calculator. So 35, enter 0.758 times 37, enter 0.242 times plus. So I get 35.5 AMU. Now, what we do is we look at the periodic table, see if we're right. Chlorine has a mass of 35.45 AMU. I said 35.5. We did chop a few sig figs, but that's how we get the average atomic mass. Now, let's do this problem in a slightly different way now. Let's try to calculate the abundance. So if we know that something exists in two isotopes, we can actually get its abundance. I'm going to round atomic masses to the 10th place again. So carbon, we're going to say exists in two isotopes because carbon-14 has a very, very low natural abundance, close to 0. So how do we calculate the abundance of each isotope? Well, in this case, I'm going to let X be the abundance of carbon-12. Therefore, 1 minus X is the abundance of carbon-13. Okay. What is the average atomic mass of carbon? It's 12.01 AMU. Okay, I'll just go out to the hundredths place here because I am rounding a little bit. And so how do we calculate the abundance? Well, it's going to be the mass of carbon-12 times its abundance plus the mass of carbon-13 times its abundance, and that equals 12.01. So let's simplify. So 12, I'm going to 12x plus 13 minus 13x is equal to 12.01. Okay, so then that means I can bring the combine the x's, right? So 12 minus 13x is going to be a minus x there, equals 12.01. So I can bring the x over to the right, and then 13 minus 12.01, this is equal to 0.99. So that means the abundance of carbon-12 is 99%, and the abundance of carbon-13 is 1%. And that is what you see when you look at the data. If you go back to the table that I showed you here, carbon-12, about 99%, carbon-13, right about 1%. And that is how we get the average atomic mass of elements in the periodic table.